In this video, I will solve the time-dependent Schrodinger equation. There are an infinite number of orthonormal solutions to the time-independent Schrodinger equation h psi equals E psi. For example, let's say this psi 0 is the wave function of the ground electronic state, and then we have h psi 0 equals E0 times psi 0. E0 is the energy of the ground state. In general, we have h psi n equals E sub n times psi sub n. And again, this is time-independent Schrodinger equation. This h does not depend on time. This psi does not depend on time. So what is the time-dependent Schrodinger equation? The form is like this. And then we can propose the following solutions. We just multiply psi 0 by a exponential function of t, e to the power of negative I times E0t over h bar. Or more generally, we have psi sub n times e to the power of negative I e sub nt over h bar. We can prove that this is indeed a solution to this time-dependent Schrodinger equation. We just plug in this wave function in here. We apply this h to this wave function, which does depend on time. It oscillates with time. And then because this h itself contains only x, y, and z, it does not contain time, we just apply this h to psi sub n. And this part, this exponential function of time, is independent of x, y, or z. This is treated as a constant. The result is simply e sub n multiplied by the original wave function. And then we can apply this IH bar delta over delta t operator to the same wave function here. And again, when we apply this delta over delta t to this wave function, because psi sub n is independent of time, so we are applying this derivative to just this exponential function of time. In the end, we get the same expression, which is e sub n times the original wave function. We compare this and this, we see that indeed this is a general solution to the time-dependent Schrodinger equation over here. But over here, pay attention, this h does not contain time. What if h contains time? When a photon induces the electronic transition of a system, the oscillating electric field of the photon, which is this epsilon with a direction times sine omega t. Epsilon is the strength of the electric field of the photon. Omega is the angular momentum of the photon. So what if this oscillating electric field interacts with the dipole moment of the system? What will happen? The electrostatic energy is this electric field times the dipole moment of the system. Note that even a hydrogen atom has a dipole moment. It's between the electron of the hydrogen atom, and the hydrogen nucleus. And then the time-dependent Schrodinger equation becomes more complicated. We have one more term here. Again, this term is the electrostatic energy of the system under the influence of the electric field of a photon over here. Without losing generality, we can take a guess of the expression of this psi. This psi is an infinite series of this general solutions to the time-dependent Schrodinger equation, in which this h does not depend on time. So this is the expression here. We need a coefficient in front of each wave function. The coefficient is c sub n, and c sub n does depend on time. So what does this mean? The squared modulus of this c sub n is the probability of finding the system in the nth excited state at time t. So this coefficient may change with time, but this coefficient does not depend on x, y, or z. So this is the expression of this wave function when the system is under the influence of the electric field of a photon. Over here, this is, again, the electrostatic energy. And then we'll have to solve this equation. What we do is we evaluate the left-hand side, we evaluate the right-hand side, and then we try to simplify the equation. So first, the left-hand side. So we apply this h plus electrostatic energy to psi. We expand the psi into this infinite series, and then we apply this h to this wave function, we got h being applied to psi sub n only, because again, this is a function of time only. This is a function of time only, and h does not depend on time. So we can actually apply this h to this psi sub n, and psi sub n does not depend on time either. Therefore, h being applied to psi sub n is en psi sub n. Over here, we simply just copy this electrostatic energy times this psi. On the right-hand side, you have IH bar times delta over delta T psi. And we expand this. Because psi sub n is a function of x, y, and z, it's not a function of time. So really, we're trying to take the first derivative of a product of two functions of time. C sub n is a function of time, and this exponential function is a function of time. So we'll have to use the product rule. And again, we use the product rule, we get two terms here. The first term contains the first derivative of C sub n. The second part contains the first derivative of this exponential function of time. So pay attention here. Over here, it's just an exponential function, so we copy the exponent here, which is negative I e sub n over h bar, and then multiply by this exponential function. And then over here we have IH bar in front of this square parenthesis. IH bar times negative I over h bar, they cancel. So really in here we have just the original wave function multiplied by e sub n. And if we compare the left-hand side and the right-hand side, they both contain this term. Over here, you have e sub n times the original wave function. Over here, e sub n times the original wave function. So again, this is the left-hand side, this is the right-hand side. In the left-hand side, we have h applied to the wave function. We get this in red. On the right-hand side, we do the first derivative of the wave function with respect to time. We obtain the same term, also in red. So this red and this red cancel. So really, we have just this electrostatic energy times the wave function equals this IH bar times psi sub n. This is time independent wave function, and times the partial derivative of the coefficient c sub n times this exponential function of time. So we have just one term on the left-hand side, one term on the right-hand side. But really, they are both infinite series. How can we simplify this? So if we focus on the left-hand side first, and for simplicity, we can just examine the very short time period, tau, immediately after the system interacts with the oscillating electric field of the photon. So in this case, there's no time for the system to change yet. Therefore, at the beginning, C sub 0 is 1. So, and C sub n is 0 if n is different from 0. So what does that mean? That means the system is mostly in the ground state. 100% in the ground state, nearly 0% in the excited state. And then, therefore, we can simplify this infinite series into just the first n equals 0 term. And then we have this guy simplified into this, just one term here. All right? So on the left-hand side, we have only one term. On the right-hand side, we still have an infinite number of terms. How can we simplify this infinite series? There's another trick. So what we do is we actually multiply both sides by the complex conjugate of the wave function of the mth excited state. So psi sub m star, psi sub m star. And then we integrate both sides. Why do we do this? It turns out if this psi sub m and psi sub n are orthogonal to each other, if we integrate this, the result will be a very interesting delta function. Delta equals 1 if m equals n. Delta equals 0 if m is different from n. So again, we're going to integrate both sides. And on the left-hand side, when we integrate this, make sure you understand this mu also does depend on x, y, and z. So we need to integrate this three terms together, the product of these three terms together. And on the right-hand side, there are only two functions that depend on x, y, and z. So this m, psi sub m, and this psi sub m. So really, we just need to integrate Again, over here, psi sub m, the complex conjugate of psi sub m. Mu is the electric dipole moment of the system. Psi sub 0, the wave function of the ground state. On the right-hand side, we need to integrate the complex conjugate of this wave function psi sub m times this wave function psi sub m. All right, and remember this integral is 0 if m is different from m. So there's only one non-zero term in this infinite series. That is when m equals m. So when that happens, we need to replace every single n with m. So this is how we simplify this infinite series into just one single term on the right-hand side. On the left-hand side, well, we can use a simplified notation for this integral. This integral is called the transition dipole moment. Again, this mu is the electric dipole moment of the system. But then if you are looking at the transition from the ground state, psi sub 0, to the mth excited state, psi sub m, and then you need to evaluate this integral with mu in the middle, and it's called the transition dipole moment. So on the left-hand side, we have this electric field of the photon times the oscillating function of the photon times the exponential function of time times the transition dipole moment. So really, it's simplified to just one term on the left and one term on the right. We don't have to deal with the infinite series anymore. And again, this mu sub 0 to m is the so-called transition dipole moment from the ground state 0 to the mth excited state. Now we can rearrange this equation because this is a differential equation. We can actually solve this differential equation first by moving this IH bar to the left-hand side, and also we need to move this guy to the left-hand side, and then we have the first derivative of the coefficient C sub m. This is the coefficient in front of the mth excited state. This coefficient may change with time. It's a function of time, and equals this complicated expression here. And now in this equation, actually time is the only variable, so I'm going to change delta to d. So dc over dt, the first derivative of the coefficient, equals this expression. And then we move dt to the right-hand side and then integrate both sides. This negative I h bar times the electric field of the photon times the transition dipole moment. This whole thing does not depend on time, so we don't have to integrate this part. This part is considered a constant. So we just need to evaluate the integral of sine omega t times this exponential function of time. If you look at this omega is the angular frequency of the photon. Omega equals 2 pi nu, and nu is the frequency of the photon. Omega is the angular frequency of the photon times this exponential function. E sub m minus E sub 0 is the energy gap between the ground state and the mth excited state. So now if we integrate the left-hand side, it's just simply the coefficient of the mth excited state at time tau. Again, tau is a very short time period. On the right-hand side, we just need to integrate this product of a sine function and an exponential function. Over here, to simplify this expression, we set omega prime to be E sub m minus E sub 0 over h bar. And then this exponential function becomes e to the power of I times omega prime times t. Because e to the power of I theta equals cosine theta plus I times sine theta, we know sine theta is e to the power of I theta minus e to the power of negative I theta over 2i. So I'm converting this guy to a combination of two exponential functions of I omega t. So over here, this part is simply sine omega t times another exponential function. I'm doing this because it's easier to integrate a exponential function. How about this part? What we're doing is we're taking the squared modulus of this coefficient. The reason is simple. this C sub m, this coefficient, does not have a physical meaning, but the squared modulus of this coefficient has a physical meaning. That is the probability of finding the system in the mth excited state at time tau. So that's why we want to integrate this whole thing and then take the squared modulus of it. So when we do that, the squared modulus of this guy is simply this. I disappears. The squared modulus of I is simply 1. And then we need to get the squared modulus of this integral, which is here. All right, and then we copy this to here, and then we evaluate this. We need to combine this two together. We have e to the power of I times omega prime plus omega times t. And we combine these two terms, and then we get minus e to the power of negative I omega prime minus omega t. All right, so again, we have two exponential functions over here. Now it's necessary to convert the exponential function back to sine and cosine functions in this format. Again, e to the power of I theta is cosine theta plus I sine theta. So we have to expand this exponential function into two terms here, and we have to expand this exponential function to these two trigonometric functions. And again, the 2i should be on the bottom here. And then we can move this 2 in here, so we have 2h bar here, and then we integrate this whole thing and then take the square modulus of it. So now we have the real part. The real part is actually the sine function plus this sine function. That's the real part, because this I, and this I cancel. And we have the imaginary part. This cosine function and this cosine function becomes the imaginary part. So but it doesn't really matter because we're taking the squared modulus of this complex function. So really it's just the real part squared plus the imaginary part divided by I and then squared. And then we need to integrate this. The integral of a cosine function is sine function. We also need to take care of the coefficient here. And minus the integral of this cosine function. The integral of this cosine function is this guy divided by the coefficient. So we have actually, this is again the imaginary part of this integral. But anyway, we're taking the squared modulus, so we have to just simply take the squared modulus of this part. And sine functions becomes cosine functions. When you integrate a sine function, you get a negative cosine function. So we got those cosine functions here. They both should have negative sign, but again, since we're squaring these two cosine functions, so the sum of these two cosine functions, so the negative sign does not really matter. Negative 1 squared is simply 1. And over here, the reason you see minus 1 here is because we are doing the integral from 0 to tau. So we plug in this tau here, and then we need to plug in 0 to here, and when you plug in 0 to here, you have cosine 0. Cosine 0 is 1, so you need to kind of take the difference between the upper limit and lower limit. Upper limit, lower limit. What about here? I didn't kind of subtract anything. This is because the sine function of 0 is simply 0. That's why. And then when we do this, we will actually square this. We will square this, and we have a cross term in the middle. We have to square this. We have to square this. And we have a cross term in the middle. So it sounds really, really complicated if we honestly expand all those expressions, but there's a trick here. So remember, when we do electronic transition, you need a UV photon, or at least a visible photon with a frequency of 10 to the power of 14 hertz. The angular frequency is 2 pi times the frequency, so roughly 10 to the power 14 or even 10 to the power 15 if you are using a UV photon. So if you look at this term, you have 10 to the power of 15 hertz on the bottom. 10 to the power of 15 hertz on the bottom. And then if you look at these two terms, and if you carefully choose a photon with the same frequency as the frequency that corresponds to the energy gap between the ground state and mth excited state, these two may cancel. And then that means this bottom, this denominator, can be much, 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 much smaller than this denominator. Again, this guy can be 10 to the power of 15. And this one can be maybe 10 to the power of 2, 10 to the power of 1. So really, if you compare these two terms, this one, the difference between omega prime and omega can be much, much, much smaller than the sum of these two. And how about the top? The top, those are sine functions or cosine functions. So if you look at the top, they are in the magnitude between -1 to 1. So really, the top parts, 1, 2, 3, 4, there are 4 top parts. They have roughly the same magnitudes from -1 to +1. But if you look at the bottom part, okay, that's different. This is much smaller than this. This is much smaller than this. So I'm going to make an approximation here. I'm going to assume this part and this part are negligible in comparison to this part and this part. And therefore, I'm simply just delete this part and this part. And I got this guy squared here and this guy squared here. So this approximation is reasonable only if omega is very close to omega prime. That means the photon energy is very close to the energy gap between the ground state and the mth excited state. And then we have this simplified expression. We can expand it. And then we have this sine something squared plus cosine something squared. That's just 1. And we have -1 squared, which is 1. So together we have a 2. And over here there's a cross term, which is -2 times cosine this guy. So we have in total just 2 minus 2 cosine this guy. And then over on the bottom, it's just the difference between omega and omega prime squared. So over here. And then if you are familiar with trigonometric functions, this part is simply just a sine function squared. This part is sine omega prime minus omega times tau divided by 2 squared. So in the end, we can put everything inside this 2 vertical bars. That means the absolute value of this whole thing squared. And there's a very clear physical meaning of this. It's simple. This is the transition probability of finding the system in the mth excited state. And it's proportional to the electric field squared. It's proportional to the transition dipole moment squared. And if the transition dipole moment is 0, the transition is forbidden. If this is non-zero, the transition is allowed. And also, there's one thing very important, that is omega prime and omega must be close to each other. That means your photon energy has to be very close to the energy gap between the ground state and the mth excited state. And then you have a significant transition from the ground state to the mth excited state. In the above derivation, I did not consider this vibrational electronic coupling or vibronic coupling. I may make another video on this topic in the future.